Good day, everyone. Today we're going to have another type of solids. This time we will be considering pyramids, area, and volume. The solids or space figures shown in figure 9.14 are pyramids. In figure 9.14a, point A is a non-complanar with square base B, C, D, and E. In figure 9.14b, the point F, the point F is non-coplanar with its base G, H, and J. In each space pyramid, the non-coplanar point is joined to each vertex as well as each point of the base. A solid pyramid results when a non-coplanar point is joined both to points on the polygon as well as to points in its interior. Point A is known as the vertex or apex of the square pyramid. Likewise, point F is the vertex or apex of the triangular pyramid. The pyramid of figure 9.14b has four triangular faces. For this reason, it is called a tetrahedron. The pyramid in figure 9.15b is a pentagonal pyramid. It has a pentagonal base. It has the vertex K and the pentagon LMNPQ as the base, and the lateral edges KL, KM, KN, KP, and KQ. Although K is called the vertex of the pyramid, there are actually six vertices: K, L, M, N, P, and Q. The sides of the bases LM, MN, NP, PQ, and QL are the base edges. All lateral faces of the pyramid are triangles. Triangle KLM is one of the five lateral faces of the pentagonal pyramid. Including the base LMNPQ, this pyramid has a total of six faces. The altitude of the pyramid of length h is the line segment from the vertex K perpendicular to the plane of the base. A regular pyramid is a pyramid whose base is a regular polygon and whose lateral edges are congruent. Suppose that a pyramid in figure 9.15 is a regular pentagonal pyramid, meaning the sides LM, MN, and P, PQ, and QL are congruent. Then, the lateral faces are necessarily congruent to each other by side equivalence. KLM is congruent to KMN, congruent to KNP, and congruent to KPQ and KQL. Each lateral face is an isosceles triangle. In the regular pyramid, the altitude joins the apex of the pyramid to the center of the regular polygon that is the base of the pyramid. The length of the altitude is the height from the center of the base or from the base, you have the perpendicular line going towards the apex, K. That is the altitude of the triangle of the pyramid. The slant height of a regular pyramid is the altitude from the vertex or the apex of the pyramid to the base of any congruent lateral faces of the regular pyramid. So from the vertex to any of the base edge of the lateral faces. In our formula and explanation, we use L to represent the length of the slant height of a regular pyramid. For the regular shaped pyramid with height 4 and edge of length 6, find the length of the slant height L. So the height from the apex to us perpendicular to the face of the base, the height is 4. Since the edge of the base is 6, we can consider this length as 6 over 2, so that is 3. And thus, we have the height is 4, half of the base is 3, and we can compute for the slant height L by applying Pythagorean theorem. In figure 9.16, it can be shown that the apothem to any side has a length 3 inches, 1/2 the length of the side of the square base. Also, the slant height is the hypotenuse of the right triangle with legs equal to the length of the altitude of the pyramid and the apothem of the base. In figure 9.16c, applying Pythagorean theorem, so the slant height L can be computed by Pythagorean theorem. So we have H is 4 and A is 3. So 3 squared plus 4 squared is 9 plus 16. So that's 25. So L squared is 25, giving us the slant height to be equal to 5 inches. In a regular pyramid, the lengths of the apothem A of the base, the altitude H, and the slant height L satisfies Pythagorean theorem. That is, L squared is equal to A squared plus H squared. Now, for surface area of a pyramid, we have the lateral surface area and the total surface area. To lay down the groundwork for the next theorem, we justify the result by taking one of the regular taking apart one of the regular pyramids and laying it out flat. Although we use regular hexagonal pyramid for this purpose, the argument is similar if the base is any regular polygon. So let us consider that we have a regular hexagonal pyramid. If we are going to deconstruct this hexagonal pyramid and laying it out flat, when the lateral faces of the regular pyramid are folded down into the plane as shown in the figure, this would be the result. The shaded lateral area is the sum of the areas of the congruent lateral faces. Using the area of a triangle, A is equal to 1/2 of base times height, we find that the area of each triangular face is 1/2 the side of the base times the slant height L. Each side of the base of the pyramid has length S and the slant height is of length L. The combined areas of the triangle gives the lateral area. Because there would be n triangles, so the lateral area is 1/2 of n times s times L, or 1/2 of L times ns. The number of side times the length of one side is the perimeter. So n times s is your perimeter. So the lateral area is now equal to 1/2 of the slant height L times the perimeter of the base. The lateral area L of a regular pyramid with slant height of L and perimeter P of the base is given by lateral surface area equal to 1/2 of the length, the slant height, and times the perimeter. Find the lateral area of the regular pentagonal pyramid in the figure 9.18a if the sides of the base measure 8 centimeters and the lateral edges measure 10 centimeters. So to analyze this, make sure that we consider pentagonal base. So we have n is 5. The edge of the base or the side of the base is 8 centimeter each. Now take note that this is the edge rather. So let's use E for that. E is 10 centimeters, but we don't have L yet. So maybe we can have or we can form a triangle with slant height L and the base edge S equal to 8 and the slant edge 10. So forming a right triangle, we can take half of 8, which is 4, slant height L, and the hypotenuse is 10. So by Pythagorean theorem, we will be having 4 squared plus L squared is 10 squared. 4 squared is 16 plus L squared equal to 100. So L squared is 100 minus 16. So that is 84. So L is the square root of 84, which can be simplified as 2 square root of 21. Now, since we know that the slant height L is 2 square root of 21 and the perimeter is NS, where N is 5 and S is 8. So we have the lateral surface area to be equal to 1/2 of 2 square root of 21 times 5 times 8. So 1/2 of 2 square root of 21 and 5 times 8 is 40. So we can cancel this out. So 40 square root of 21 square centimeters, which is equivalent to 183.3 square centimeters. It may be easier to find the lateral area of a regular pyramid without using the formula of Theorem 9.2.2. Simply find the area of one lateral face and multiply by the number of faces. In example 2, The area of each triangular face is 1/2 of base times the height. So that would be 1/2 of the base, which is 8, and the height, which is 2 square root of 21. So 1/2 base times the height, or simply 8 square root of 21. So this is the area of one triangular face. Thus, the lateral area of the regular pentagonal pyramid is 5 times 8 square root of 21, which is 40 square root of 21 square centimeters. The total area, or the total surface area T of a pyramid with lateral area L and base area B is given by T equal to L, the lateral surface area, plus the base area B. The formula for the total area T of the pyramid can be written as T equal to 1/2 of the slant height L times P plus the base area. The pyramid in figure 9.2 is a regular square pyramid rather than just a square pyramid. It has congruent lateral edges and congruent lateral faces. So regular square pyramid. Regular polygon as bases. The pyramid shown in figure 9.2b is an oblique, and the oblique square pyramid has neither congruent lateral edges nor congruent lateral faces. It has congruent base, it has symmetric base, however, the edges are not congruent. For the volume of the pyramid, the factor 1/3 in the formula for the volume of the pyramid provides exact results. This formula can be applied to any pyramid, even one is not regular. In figure 9.2b or 9.20b, the length of the altitude is the perpendicular distance from the vertex of the plane to the square base. The volume V of a pyramid having a base area B and an altitude of length h is given by V equal to 1/3 of the base area B times the height. For example, find the volume of a regular square pyramid with height 4 inches and base edges of length S equal to 6 inches. So we are given with the height equal to 4 inch and the base is a square of side 6 inches. So the base area is given by S squared. So the base area is 6 squared equal to 36 square inches. Since the volume is given by 1/3 of base times height, so that would be 1/3 of 36 times 4. So 36 over 3 is 12 times 4. So the volume is 48 cubic inches. To find the volume of a pyramid by using the formula V equal to 1/3 base times height, it is often necessary to determine B or H from other information that has been provided. Table 9.1 reminds us of the types of unit necessary in different types of application requiring measures. For a linear measurement, it would be length of segments such as length of the slant height. The unit is in inch, centimeter, or foot. For area, which is the amount of plane region enclosed, such as area of lateral face, it should be in square inches, square centimeters, and square foot. While for volume, the amount of space enclosed, such as volume of a pyramid, the unit would be cubic inches, cubic centimeters, and cubic foot. In a regular pyramid, the lengths of altitude h, radius r of the base, and lateral edge e satisfies the Pythagorean theorem that is e squared is equal to h squared plus r squared. The frustum of a pyramid is a portion of a pyramid that lies between its base and a parallel plane that intersects the pyramid. Plane and solid figures may have line symmetry and point symmetry. However, solid figures may also have plane symmetry. To have this type of symmetry, a plane can be drawn for which each part of the space figure has a corresponding point on the opposite side of the plane at the same distance from the plane. Each solid in figure 9.25 has more than one plane of symmetry. In figure 9.25b at 9.25a, the plane of symmetry shown is determined by the midpoints of the indicated edge of the box. So this is the plane of symmetry. In figure 9.25b, the plane determined by the apex and the midpoint of the opposite sides of the square base leads to a plane symmetry for the pyramid.